fourth and final video on linear regression. In this particular video, we're going to focus on determining if our regression equation is significant or not. So in the previous video, we learned how to calculate the coefficient of determination, r squared, based on our data. And in order to do this, we need to calculate out a series of sum of squares. And we know that if we have two of these sum of squares, we can calculate the third. Now, in order to calculate significance of our analysis, we can use a procedure similar to ANOVA. So if you are comfortable with the significance test using ANOVA, in which to calculate the F value, compare that to the F table, then you should be in really good shape for calculating significance for linear regression. If this is something you're uncomfortable with or you don't remember, it might be advantageous to go back and watch those videos. But we're going to cover through an example here in this video, and then we're also going to go through some examples in class. So here we've got our data, salinity versus length of our animals. We've got our regression model with regards to the best fit line equation. And in order to test our significance, again, we are testing specific hypotheses. So our null hypothesis in this particular instance is that our slope equals 0, and then our alternative hypothesis is going to be our slope does not equal 0. Now the reason for this particular null hypothesis is that if we're thinking about the basis of linear regression, it's this idea of a cause and effect relationship between an independent variable and a dependent variable. So if there is some type of a cause and effect relationship, well then the independent variable or the predictor variable needs to be part of our model. And if the slope of our line equals 0, if b equals 0, well then it's going to lead to all of our x's equaling 0 when we're making our predictions for y, and then in turn it's indicating that the value of y is just random. It doesn't depend on x. And so in turn, again, we're testing against this null hypothesis. And if we reject the null hypothesis, then we conclude that the slope is not equal to 0 and that we should be including x in the model because it's explaining variability in y. So how do we go about doing this? Well, we're going to set up a table that's very similar to that of our ANOVA. So we have some different columns here that we're going to fill in. We're going to use these to calculate an F value, and that F value is going to be tested against a critical value, and then we're going to use that to determine if our model is significant or not. So the first column here is our sum of squares column, and we're going to fill this in with the information that we use to calculate our r squared values. So we have our regression sum of squares, our residual or our error sum of squares, and our total sum of squares. So these are values that we calculated in the example from the previous video, so we're not going to go back and do so. After this, we need to determine what our degrees of freedom are. So in order to do this for our simple linear regression model, we only have one factor that we're testing for our independent variables. So the degrees of freedom for x is just going to be 1. And then for our error and for our total, those degrees of freedom are going to be n minus 2 and n minus 1. And again, these are going to be the data pairs, not the total number of data points. So this is going to be 8 and 9 for our respective example. For the mean sum of squares, just like ANOVA, we're going to take the sum of squares and we're going to divide it by our degrees of freedom. So for our regression for x, we're just simply taking the sum of squares dividing by 1, and then for the residual, we're taking the sum of squares and dividing by 8. So we can go through and calculate those values, and just like ANOVA, our F value is going to be the mean sum of squares of our regression model of x over our mean sum of squares of the error, or the residual. And so we can go through and calculate out this F value, and then we would then take this and compare it to our F table. Now again, our F distribution has two different degrees of freedom, and we're using the numerator and the denominator in which to determine this. Our numerator here is x, and our denominator is the residual. So we can go through and we can look through our F table and we can get our critical value. We're not going through this in the video because we've done this several times in these videos and we'll be covering this in class. And then we compare our F value to the critical value, and because our F value is greater than the critical value, we can safely say that we reject the null hypothesis and that the slope does not equal 0. And in turn, this means that X should be in the model because it's helping to explain variation in Y. Now, we went through this quickly. We'll spend some time in class going over this, but my suggestion is to go to section 14.4 of the text to make sure you feel comfortable, and then to go through practice exercises 14.1 to 14.4 so you get comfortable through the whole process that we talked about in these last 4 videos. This marks the end of our coverage of linear regression, and so some important things that you should know, the main differences between correlation and regression, the different parts of the linear regression model, the slope, the intercept, the residual, how to calculate the slope and the y-intercept for regression so that way you have that linear regression equation, how to make predictions of unknown values of y based on the regression model and providing values of x, how to determine r squared, and then also how to determine if the regression model is significant or not using that same model that we do for ANOVA. So as we move forward for the rest of the semester, we're going to start talking about some topics that we've previously covered, but we're going to start discussing what happens when we start to violate some of the assumptions that we make for these tests.